So just as with our other disciplines that we have studied, electrical engineering has a wide range of possible areas of focus. We can be looking at microchips and the flow of electricity through a computer, all the way up to the flow of electricity in the power grid, and kind of everything in between. For our focus, we're going to be looking at just pretty basic circuits with a load and a resistor, and then eventually with multiple resistors and multiple loops. So to make sure that we review a little bit of our physics before we get started here to make sure that we're in good shape, I've got those in front of us here. So for example, when we talk about the charge, that's carried by electrons, and that's measured in coulombs. And so when the charge on an electron is very, very small, on an individual electron, 1 times 10 to the negative 19th coulombs. Conservation of charge. The number of electrons that are entering a junction is equal to the number that are leaving the junction. This becomes extremely important when we start to look at more complicated circuits that have multiple loops and multiple voltage sources, where we need to build a system of equations in order to be able to solve for the various currents flowing in the various parts of the circuit. So that conservation of charge is an important piece. Current is measured in amperes or amps, and so that is a measure of the flow of charge through a circuit. So we can think of it as coulombs per second. 1 coulomb per second is equal to 1 amp. Voltage, which is a measure of the difference between areas of low potential and high potential. So like a battery or some sort of power source is going to provide voltage, which is going to drive the flow of electrons through the circuit. You can think of it as kind of like a pressure, like in a water pressure in a hose, something like that. And so electrons flow from a high potential to an area of low potential. And so this creates the battery or other voltage source creates this pressure. And then finally, we have resistance. So whenever we have a load in a circuit, whether that's just something as simple as a resistor, or something like a light bulb or a heater or some element that is we're trying to power by the electricity, provides resistance in the circuit. And so that is measured in ohms. And depending on their resistance, materials can be referred to as insulators. So if they are highly resistive to electron flow, charge flow, conductors, semiconductors, and then ultimately superconductors, where the flow of electrons, the flow of charge is almost unimpeded. One thing I should point out is that the flow of electrons as diagrammed in our circuits is actually backwards. This all goes back to Ben Franklin way back in the day. But in our diagrams, we will show current is flowing from the positive terminal out, when in reality it's flowing in the opposite direction, because we now know electrons are negatively charged. So the flow of electrons is going from the negative terminal into the positive in the actual flow. But for our purposes, we will stick with the conventional and make sure that we understand it that way. And so in this simple circuit, electrons would be flowing out of the positive terminal through the resistor and then back into through the negative terminal for our diagramming purposes, even though in reality we know it is opposite. So I made mention of it already, but we can analogize the flow of current through a circuit similar to what's going on with water flowing through a pump and a series of pipes or a hose. And so as water flows through the pipe, it does experience energy dissipation. So some of the energy in the flow is dissipated because of the contact with the walls. We'll study this in our mechanical engineering chapter, a couple equations related to the flow of fluid within a pipe. But there's that friction, that resistance. So we can think of that as being the resistance that the electrons experience when flowing through a circuit. And so then the magnitude of the pressure that drives the flow of the water, the pump, for example, is essentially what the battery provides. And so that's kind of the analogy that we can use to describe a circuit in something that's a little bit more tangible, more physical, that we can put our heads around. So if we look at the analogy here, so the pressure, again, that the pump is providing is going to be the voltage source, the battery, the motor, whatever it might be. The flow rate of the water in the hose is the equivalent of the current that's flowing through the wire. The hydraulic resistance that I mentioned, so the drag on the water flowing through the pipe, is the equivalent of the electrical resistance, whether that's a resistor or some other type of load that's within the circuit. And then the last thing is the power. So the power in the stream, which is, we'll define that term a little bit more carefully in a minute, but the power in a stream is equal to the pressure drop times the flow rate. So in the stream, in the hose, so whatever that pressure drop is from point A to point B times the flow rate is going to calculate the power, the mechanical power of the water. And so for electrical power, we can calculate it by multiplying the voltage drop times the current. So that gives us the power law. Again, we'll take a look at that in just a moment. And so the relationship between current and voltage and resistance is governed by Ohm's law. Power we'll get to in a second with the power law, but Ohm's law says that the voltage is equal to the current times the resistance. So whatever the current is flowing through a resistor or a load times the resistance that in ohms, the measured resistance, that's equal to the voltage drop across that load. So in front of us here we see a simple circuit with a 12-volt battery source providing a 12-volt difference between the low potential negative side and the high potential positive side. We have the current that's flowing through the circuit through the resistor here that has a resistance of 10 ohms. And so we want to figure out what is the value of that current, and so we can do that simply enough using Ohm's law, V equals I times R. So the 12-volt source, that's equal to the current times the 10 ohm resistor. So if we just divide both sides by 10, we can easily enough arrive at a current of, and if we use significant figures here, we can see we've got 2 everywhere, of 1.2, whoops, not ohms, but amps. And so again, I've made mention of it already, but we have this power law. So in our chapter on energy conversion, we were introduced to this power law, so we'll make use of it a second time here. And so it connects the voltage and current to electrical power, which is analogous to mechanical power. And so the equation for electrical power is the current times the voltage. So taken together with Ohm's law, we can connect the 4 variables: the voltage, the resistance, the current, and the power that a circuit produces. So in our last example here, we've got a circuit that has a 9-volt battery source. So we can sketch that here with our positive and negative. We have a wire, and then we just have a simple resistor. So we can sketch that out. Our battery has a voltage of 9 volts that it's supplying to the circuit. And then it says that the resistor dissipates power of 50 watts. So those are the same watts that we studied before. So remember, that's a joules per second measurement. So it's just an electrical version of that. Same units, just in the context of a circuit, it's in terms of amps and voltage instead of joules and seconds. So it says here that we want to find what's the current in the wire. So that's where we're going to start with our power law right here. So we've got a power of 50 watts is equal to our current, which we're trying to find, times our voltage of 9.0 volts. So if we divide both sides by 9, we're going to get a current, again measured in amps, of, if we round to the nearest tenth, 2 decimal places, of 5.6 amps. And so then once we have that, we're asked to find what the resistance in our circuit is. Well, for that, we can use Ohm's law. So that's our V equals I times R. So we still have the same voltage of 9 volts is equal to our current that we just found, that 5.6 amps, times our resistance. So if we scroll down a little bit, we can divide both sides by 5.6, and we'll eventually end up with a resistance, if we push buttons on our calculator, of 1.6 ohms. Again, sticking with our 2 significant figures. So this is how we can connect those 4 variables with those 2 laws: the power law, current times voltage, and Ohm's law, voltage is current times resistance.